let's say, and also let's say generative models. So I will briefly present the transformers and then go a little bit more into details of how LLMs are created and adapted. And then I will list some challenges in data acquisition and in high performance computing. So I'm, as Priyanka presented me, I'm the head of Machine Learning and Language Technology Lab. So we work a lot on the research of LLMs since 2018. We have really many, let's say, basic research and also applied in many areas concerning natural language processing. And some of them, interesting one, also together with the Basant, who is kindly invited me here together with Priyanka. Okay, so let's start with a little bit of basics. So language models, what they are. So language model is basically machine learning model which tries to compute the probability of a word sequence. So for example, let's have a sequence of words like words, let's say 1 to n, and we try to predict that, right? It can be a sentence, it can be a document. The model who can do that would be, it's called language model, right? So what would that be used for? For example, if we are in machine translation and have two snippets of text like high wind tonight and large winds tonight, then if this one is more probable, then machine translation engine would suggest that high winds tonight is the correct translation, for example. So you see that there are really many possible uses. So how do we compute this in the next word in a sequence? So we have different ways how to do it. So typically, generative models predict the next word in a sequence. So for example, we have the word index I, and we have previously I minus 1 words. Then based on this conditional probability, we predict the next word. So for example, if they say they attended the international, let's say, summer school or event, so any sentence we find on the internet or whatever source do we have as information can serve as the training set for that. You can see we can take 1 word, 2 words, 3 words, and then predict the next one and the next one and the next one, right? So the abundance of data for that exists from the text on the internet. Or alternatively, we can also compute the masked word in a sequence. So for example, we have one of the words and in between and the next words, previous and the next words, and then predict this in between word. We call it masked word, and for that we also have lots of data. So in spite of, let's say, troubles, they visited the online lectures. So so the model which can do that, you see, is called language model, and if it's very large and uses, let's say, transformers, or if it uses neural network, then it's called large language model. So so all the knowledge of a large language model is in these conditional probabilities, right? So all the reasoning, all the translation capabilities, generative capabilities, it has to be stored in these conditional probabilities. So that means that the neural network which is used nowadays typically for that, will have to store that conditional probability, really long chains, so that we can predict successfully and generate successfully. So yeah, so as I mentioned, we use transformer architecture of neural networks for that. That is currently the most successful deep neural network architecture. I mean, for a reason, because it's architecture which is heavily tailored to current generation of high performance computing. It's non-recurrent. It is encoder decoder. It can be used only encoders as an encoder or also only as the decoder. But it has fixed input length. That means if it has fixed input length, we can map that to the high performance computing, let's say for the GPUs. So this input is long, but then internally it's projected to a shorter dimension for computational reasons. It's heavily adapted for parallel processing, and it's really, as we'll see later, it's heavily adapted for extreme parallelization. That means that everything can be computed as dot products or matrix operations. So as computer scientists, we know that matrix operations are really, let's say, prohibitively costly. Let's say O of n to the 3, right? So cubic. But we still do it in GPUs, right? Because it's fast and it's projected to small fixed dimensions, and then it's computationally very efficient. So let's say technological novelty. These are technological novelty, but in the context sense, the novelty is the representation. It's based on the extreme use of attention, and I will explain that a little bit later. So it's very well scalable. We can have hundreds of layers in these deep neural networks, and that's why we have these really, really huge models, as you will see. There are also some other technical details, like it includes level jumping to prevent forgetting, or problems with the vanishing or exploding gradients. So let's see this transformer, right? So you probably know these architectures, you have seen it. So how it works, we have the input, we have some embeddings for that, we add positional encoding, then we have several layers where we have this attention, normalization, feed-forward neural network. So this encoder, once we have this encoder prepared, that means the representation is stored here, we can start decoding that. Let's say in machine translation, we would put the input here, it would be represented in the original language here, and then we would start to decode it into another language. And this representation would inform the decoding into another language. So because we have here, this is a little bit of architectural changes, because between encoder and decoder, because here we have also the part which helps us in generating. So we have a linear layer which basically selects these probabilities, and then softmax to get the probabilities and select the output. Right, so that's a famous paper from 2017. Initially, this was machine translation, and the model basically predicts each translated word. So if I go a little bit into detail in this encoder-decoder, so as I mentioned, in machine translation, which was the original motivation, so we have, let's say, in French, je suis étudiant. We put this to several encoder layers, we have the representation, and then we start decoding to several layers of the decoder, and then we produce one word at a time on the output. So yeah, so let's see the encoder first. So two things are really important here. One is the self-attention, which I mentioned is used for building a really successful representation of the words. So neural networks can only process numerical input, and the text is symbolic, right? So we have to turn these symbols into numerical values so the neural networks will be able to do that. And to have this presentation really informative, right? So that we will know for all the words dependency with all the other words, and the language is strongly dependent of, I mean, the meaning of the sentence can depend on all the words, right? That means that we need mechanisms where this is happening, and this is called self-attention in the transformers. After we have this successful representation, we use feed-forward neural networks, let's say 1 or 2 layers, so that we basically do something with that representation, push that forward, let's say our goal, what we want to do, in this case language model, to, let's say, predict the next word. So this is the architecture, right? So as you see, there's no weight sharing between different encoders. So each word has one such block of encoders. So what happens, all these interchanges are local, right? So all this is, I mean, attention is, of course, going across the words, but other layers are as much independent from as possible from one another, so that we can process them successfully in a parallel mode, right? So this is how it looks when we start. So when we start, we have several words on the input, let's say in French. We compute their embeddings. So you see they are relatively large vectors. Now we compute their representation with self-attention. Then we get another representation, let's say enriched representation, and this goes into the feed-forward layer, right? So we try to keep that as separate as possible. So this is how the encoder top-level view looks like. So we have embedding, that means a vector for each word. The machine, I mean, the network doesn't know the position of each word. So if these words would be interchanged, the meaning would be different, but the neural network wouldn't know about it. So we add some positional encoding. We add information where each word is. Basically, we add some pattern, which is, I mean, let's say the first word has one pattern, the second word has a little bit different pattern, and so on and so on. So we put through this neural network, so self-attention, normalization, feed-forward, again normalization, and you also see we have this jump connections, which basically means that this representation can also bypass the self-attention so that we don't lose the information, that we still get gradients when we do the training. So let me illustrate this self-attention. So let's suppose that we have the sentence like the animal didn't cross the street because it was too tired, right? So we want to build a presentation for each of these words. For some of them, they have some inherent meaning, but yeah, the meaning can be is always contextual in language, right? So the animal in this case is concrete animal. It could be, let's say, party animal, whatever. So we have to build this representation, and especially for the words like it. So what it refers to. So it could refer to the animal, or it could refer if the sentence would be a little bit different. So if the sentence were the animal didn't cross the street because it was too wide, then this it would refer to the street, right? So we have to bake in this representation, this context into each word, and this is what we call the self-attention. So if we illustrate how this works, so for example, for the word like it, you see it gets most of its representation from the animal, right? It also gets representation from other words, and this is what happens for every word. So every word gets informed by all the others. This is what is called self-attention. It's computationally demanding, right? So we have to compute basically the quadratic, quadratic numbers of this, let's say, dot products, right, to get this. But still, it is worthy because you get really informative representation, and this is the crucial innovation in the transformer architecture. So how it works, this self-attention, so let's have that we have two words for simplicity's sake, we get their embeddings. So now, because it has to be efficient, right, we project that, we use for each of these inputs, we have a projection matrix, three projection matrix basically, right? So we project each of these words into vectors Q, K, and V, so query, key, and value. And with these three, let's say, much shorter vectors, basically we use them to compute this self-attention in an efficient way on the GPUs, right? So we'll see how it works, right? So for example, we start with the, let's say, one word. So we have embeddings. We have now three projected vectors, which are still related to this X, right? Because we projected them in such a way that they basically keep the essence of the meaning. Now we multiply this query vector with all the other keys. So query goes with key 1, query goes with key 2, and so on. And now the results of these dot products, right, they will basically constitute the meaning of the word x1 enriched with all the other meanings, right? So that's how it's supposed to be. And this is how it is, right? So we have these products, we normalize them so that this number don't get too large, and then we apply softmax. So for example, in this case, you see that the first word gets 88% of the meaning from itself and 12% of the meaning from the machines, right? So and once we have this, we use the values, which are actually our representation, to get this part, right? So this key and query are used to compute how much of each value do we want to have stored, and value is basically the representation. So we take basically 88% of V1 and 12% of V2 and store them into the vector. So this is now our representation, which we used in the next layer, right? So basically, this is I mean, in the principle, these are matrix calculations. Sorry. Because right, we have many words, and these dot products are basically just grouped together and put into the matrix. So this projection matrix is multiplied by basically by x to get the q, the query, the key, and value. And finally, once we have this, so we have computed multiplied q by key, so that we know how much of this value do we get. We normalize that and multiply with the v to get its actual representation z, right? So that's self-attention. So of course, we do this several times, right? So for example, previously we showed this representation for it. So this is the representation how all the other words affected. But we do this several times. Basically, we use what is called several attention heads, because one word can have different meanings in different connotations. So, for example, one of these heads would compute probably with the representation of the animal if it's crossing the street, otherwise if it's doing something else. So it's not something which is very comprehensive. It's also, but it turns out that if we have more complex text, then more attention heads help, and we get more rich representation and more successful for the downstream tasks. So this is the summary, right? So we have our axis. We compute their projection matrices, the vectors q, key, and value, set for many of them for several attention heads. We get these z's, we merge them together, and we have representation for the next layer. And this is repeated not with the original x vector, but with the projected on the next layer, and on the next, and on the next, and so on, right? Right, so the decoder is pretty similar. The only difference in the decoder is that we get this last layer attention, this last layer, basically vectors into the what is called encoder decoder attention, and this informs all the layers of the decoder, so that we know what was generated here. So what type of representation do we have here? So this is how it works. I hope you see the animation. So vectors, I mean, the input are the strings. We project them into numerical embeddings. We add the positional encodings. Then this goes through several layers of the encoder. The key and values are basically supplied to the decoder, which can produce one word at a time on the output. Right. So in this case, we produced, for example, the first word, let's say I, and then this goes into the next layer, and only decoder then starts to work. We have this representation stored, and now we generate one word at a time. The previously generated word goes onto the input, so that we know what we generated. This provides additional context, and we proceed through the steps and generate the whole sentence in the decoder. Right, so I mean, we proceed that as long as we generate a special token called, let's say, end of sentence. So that's how long the generator works. So of course, we don't need encoder and decoder in all the transformers models, in all large language models. So we can use just the encoder, for example, for the text classification. We'll see that in the models called BERT. Or we can use just the decoders. This is used, for example, in the generator models like GPT. So let me show you animation. I hope you will see it. So we have the input. It's basically we compute this self-attention. All the words inform all the others. This is repeated through several layers, let's say even hundreds of layers. So in this case, 3 layers. Now we start decoding. These words inform the decoding, and now the previously generated words also inform the next word. So we proceed this through several layers of the decoder, and we get these rich representations, and let's say hopefully also useful outputs, right? In this case, for the machine translation. Right, so I mentioned that we add positional encoding, so that's something we have to do so that the network knows the position of each word, because the language is highly contextual. The position is important for many languages, for most of the languages, I would say. So what is the positional encodings? There are some special vectors which basically encode the position. So for example, this is the pattern for the position 1, the pattern for the position 2, for the position 3, and so on. So in the principle, these patterns are typically generated from sinuses and cosinuses. So in this case, the pattern could look something like this, right? So how do we produce the output? So the last component, which is still missing. So basically, in the last, we have this linear layer, which takes the last layer of the transformer decoder, then produces these logits as the, let's say, one for each words in the vocabulary. And then we apply to that softmax, getting probability for these logits. And then we basically sample from them, or take it greedy, the most probable one, to generate the word, let's say M in this case, on the index 5. So this is how the encoder works. So how do we train the transformer? So we basically put a lot of text through that, and we have, let's say, if we have a very small vocabulary, like in this case, each word has its own index, and we predict the index, the probability of each index. So in reality, this output indexes are much considerably longer, let's say, on the order of, say, 50,000 words or 100, even 100,000 words, which we are trying to predict, let's say, tokens, not words. So the last function which we use is typically, let's say, cross entropy or Kullback-Leibler divergence. So yeah, we are outputting probability distribution. The true output is one hot encoding. We compute the difference between these two guys, and then this guides our training. This is our loss function, which we use in the gradient descent. So yeah, so typically, of course, we don't compute loss just for a single word, but for the whole sequence. So we basically compute this, let's say, correct word and compare that with the, let's say, softmax output, so the probabilities. We compute the difference and sum it together to get the information for the gradient descent. Right. So this is our transformer architecture. It should be much clearer now what we are doing, right? So we have encoder here. We do the representation in the multi-height attention. Then we enrich that with feed-forward, let's say, neural network. We repeat that for several times. That's the tens or even 100 times. And once we have this representation, we can go to the decoding, and then we generate things on the output. So yeah, so maybe I can skip that. It's not that important. So a few hints for the transformers. So we use this input tokens are basically statistically determined. We typically store several checkpoints during training, and then we can also average them to get better results. We use gradient descent, basically a package called Adam, which does the optimization with learning rate changes, so dynamically. We also apply dropout. That means we randomly hide a portion of, let's say, connections during training, so that the training doesn't get too dependent on individual components of the transformer. I mean, the knowledge is more distributed because each time, let's say, 10% of the weights are missing, so we have to distribute the knowledge better and make it more robust. So we do things like label smoothing, and yeah, in the decodecs we use beam search instead of just selecting greedily. So yeah, let's see that. So transformers are nowadays used everywhere. So we, for example, in music, instead of tokens, we can use, let's say, MIDI forces, velocity. We can use that in object detection when we compute attention between the pixels or parts of images. In time series, we store, for example, things like parts of the signals as discretized values and freedom as letters. So, for example, yeah, in image selection, basically, we can take parts of the images or even the pixels as the letters and then compute this attention between them. So this works very well. It's probably the most successful architecture right now. And because it's highly parallelizable, it can also run very efficiently on the GPUs. So if we now go a little bit for the text processing part more deeply, so learning goes in two phases. So the first phase is pre-training, where we basically use, let's say, huge amount of text to predict the masked word or the next word. And the training is long. We need, let's say, really strong machines for that. But once we have that, we have learned a lot about the language, right? So in the second phase, where we fine-tune the large language model for the specific task, it's much more efficient, right? So we know everything about the language. We have this conditional probability, how things work in the word, and then we can just be specific for our task. It's much faster. We transfer the knowledge about the language and the word from the first phase, and luckily, there are many pre-trained languages which are now publicly available, also for less resource languages such as Slovene. And yeah, I know that there are also lots of languages for Hindi and other Indian languages. So in principle, we have three flavors of transformers. One used only encoder, another one used both encoder and decoder. For example, in machine translation, this is called T5 models, so text-to-text transfer transformers. And the most popular recently are so-called decoder models or GPT models, so generative pre-trained transformers. And I will speak about BERT and GPT a little bit more. So BERT uses only the encoder. It combines basically two tasks. First, it predicts the mask words in a sentence, and then it also predicts the order of the sentence. So it has two sentences on the input, and it tries to predict whether the sentence A is followed by the actual sentence B in some real text or not, right? So in this way, we get a little bit more inter-sentence dependency, not just intra-sentence dependencies between words. So yeah, some of the BERT variants don't use the second task. They only use the mask words. So so this is, I mean, typically when we have this representation, then we use this and fine-tune that for some classification tasks. So BERT models are typically used for classification tasks, or let's say for the sequence labeling task. And nowadays there are several multilingual variants. For multilingual BERT, for example, supports 104 languages by training on Wikipedia text and some other text. And let's say this is a little bit outdated, comes from 2018. The new architecture called modern BERT is now maybe even more efficient and but uses much more text and much more training data. So there are many publicly available BERT models, let's say on Hugging Face and other let's say repositories. So how do we use BERT? So for example, if we want to predict, let's say, the sentiment or grammatical correctness of the sentence, what do? We put the tokens of a sentence on the input, or the text. It's not necessarily the sentence. This could be, let's say, a paragraph. Then we compute the embeddings and everything else. This goes through the whole BERT. And because this is classification task, we can select one specific position. It's typically position 1. So, and on this position, basically, we use it to fine-tune the model to predict something. Let's say to predict whether this is a positive or negative sentiment. That means that we put sentences on the input, we know what the output should be, and then we basically change the weight according to whether the output is correct or not. So we can do that for many other tasks in a similar way. So basically, if we use classification, if we use sequence labeling, then this is the way to go. Considerably much better, typically much better than using the GPT models, which are much larger and less efficient computationally. So how can we use these models, let's say in a multilingual sense? I think we're all interested in that. So in pre-training, we basically want to train the neural networks, the transformer models, which are composed of several matrices, right? So we use this matrix representation here. So we put lots of text of different genres, of different languages, and we basically train this and get the matrix, multilingual matrix, right? Which knows about lots of text, lots of languages. Now, if we want to do fine-tuning for a specific use case, let's say for the sentiment, what do? We take this matrix, we let's say train it or fine-tune it specifically for one task, let's say sentiment of the news in, I don't know, let's say in English, because we have lots of resources in English. We do this training, we still have a multilingual model, but now it's fine-tuned for the sentiment prediction. If we want to use it in English, fine, we can do it directly, but we can also use it for other languages. For example, we can take that model, put the Slovene or Hindi sentence on the input, and the model will also work pretty well. Maybe not perfectly, but good enough, and that's good for many multilingual I mean, that can work for many multilingual tasks. So, of course, if we have a few sentences in Hindi or Slovene, we can adapt that, and the model would work even better. So this gives us the question, so why don't we just use only multilingual models? So this is, so the performance of many tasks drops a little bit with more languages. So for example, here's an example of one of our studies when we try for different tasks like named entity recognition, part of speech tagging, dependency parsing, sentiment analysis, and word analogy. And you can see that monolingual model, in this case, Slovene model, was somehow better than these two models, which are, let's say, which have 100 languages, right? So, and this difference can be considered, right? So yeah, it still makes sense to train, let's say, monolingual models. And if you cannot do monolingual models, then at least few lingual models. So the reason why this is useful are vocabularies in large language models. So for example, so vocabulary is constructed statistically. So we see which pieces of text appear most frequently together. So I have an example here of a sentence. Okay, it's a sentence in Slovene, but doesn't matter in any language. So monolingual model would turn this into 10 tokens. So this would be the tokens, right, of the sentence. But if you would use, let's say, multilingual BERT, which knows about 100 languages, it would use 17 tokens for that. So you see, it has to split the sentence much more fine-grained because it doesn't have this specific language-specific tokens, right, which are more informative. It has to build this semantics through several layers of the transformer, right? So it loses some information, it loses some performance. So a little bit of trade-off are so-called few lingual models, which capture not just one language, not 100 languages, but something in between. So yeah, what's good for that? We have more data for training than for a single language, but we can also make more specific dictionary of these subword tokens, which is very good for cross-lingual transfer. So for example, there are a few trilingual models. We built a few of them for European languages, but they're also bilingual and few lingual models. So for example, some of them for the Slovene, and also with the our colleague, Professor Basant Agrawal, we built basically models for Hindi, English, based on the Indian languages, and just English, Hindi for just for English and Hindi, right? So, for example, we use that in the code mixed affective task quite successfully, these models. So there is some benefit of that, right? So how do we typically do adaptations for the task in BERT? So what we use is called lower rank approximation. So basically, when we fine-tuned weights, we take the pre-trained weights and we don't change the whole. We just change a little bit of them. It's not necessary that we change all of them. We change some of them, and we call this, I mean, we use that a trick. So that we use the matrices which are low ranked. So this updated weights, they are basically for this we used decomposed matrices, as it's shown here, which are of considerably lower rank, has less weights, so that we can learn them faster, and then we inject these weights somewhere in the transformer. Not necessarily on all the positions, but some of the, let's say, matrices are modified, and that's sufficient so that we get adaptation for the specific task. Yeah, so also of particular use nowadays are so-called decoder models. So GPT models are the most known, but there are lots of other models. Many of them are free. Let's say Gemma from Google, Llama from Meta, Mistral, Bloom, Olmo, many other models. Almost, for example, is interesting because it has everything in public domain, so you can see how it works, what was the data used, and so on. So it's pretty much the same, but it only used the decoder blocks, right? So it only used the decoder. But decoders can then be larger, longer, and deeper, right? So these generative models are called autoregressive generators because they somehow prime the generator with the context. So when you ask something to the ChatGPT, that's like putting this question at the beginning of the generator, right? And from this, if this is the question, now the generating starts from this point onwards, right? So here we start generating, let's say the next word and the next word. And as you see, attention is basically goes just forward, right? So we don't use the attention to the next layers because they were not generated yet, right? So that's why it's called autoregressive generators. So the presentation is a little bit different, but yeah, it's still the typically let's say self-attention. Okay, so for getting these large models, we need huge amounts of data, and the models are larger and larger. So basically, the size of them goes almost exponentially. So if I illustrate that for the GPT-2 and GPT-3 models, so two of the models were which were the parameters were still published. So so for example, GPT-2 used 48 layers and 25 attention heads, and GPT-3, which was basically a year later, already has 96 layers and 96 attention heads. So the representation, the initial embeddings was 1600, let's say, dimensions of the vectors, and the key value in Q vectors were of dimension 64. In GPT-3, this was increased by tenfold, and the internal representation changed was doubled. The context size, that means how many tokens you can put on the input, here was 2000. Initially, it was 1000. And this gave altogether, let's say, 1.5 billion parameters. And this was already 175 billion parameters. Now, GPT-4 and ChatGPT are known to be much larger. So there are some rumors around, but typically it is known that they use around 220 billion parameters times 8. That means there are, let's say, 8 models with the mixture of experts, each of them of approximately 220 billion parameters. So over 1 trillion parameters altogether. So yeah, we have these huge models, right? So there are some technical differences. So we also train them, besides predicting the next word, we also train them so that they do what is called instruction following. So basically, they use, let's say, collection of the task of the questions, let's say around between 50 and 100,000, so that the model is getting chatty, so that it learns how to answer the question, that it learns to solve a specific task. For example, machine translation, question answering, sentiment, or whatever you want. You train the model to do that in this instruction following data set. And you also do what is called preference adaptation. So you train the model to tell it what type of input you want. So this is typically done with the human feedback, and there are quite some data sets for that. This is considerably slower. It uses reinforcement learning. So it's not done on the whole network, it's done on the part of the network, so to be still computationally, let's say, acceptable. So this, we all know, had huge public impact. It's disruptive for all writing professions, including learning, teaching, scientific writing, many businesses, right? And it also brings us new areas like prompt engineering. So prompt engineering is something which is now, when we use the models directly, we don't have to fine tune them. We just give them different instructions. So why it works? So it works because of these conditional probabilities in large language models, right? So these prompts are basically the conditional probabilities, but the model, based on that, through the self-attention, can generate the answer, right? So that's the idea. So yeah, so it's a sort of soft science, if it's science at all. There's a lot of things we don't know yet, why certain prompts work and why not. But there are also lots of tools and techniques which help us to be more efficient. So I selected this, let's say, web guide, like prompting guide, which has really many techniques in prompt engineering and can help you in designing and automating the prompt engineering process. So yeah, LLMs are really data hungry. I would also want to speak a little bit about how we build LLMs. So this is the graph from the Llama 2 model, which is publicly available. So we see that even after 2,000 of tokens, basically 2 trillion of tokens, the training loss still goes down, right? So that means 2 trillion tokens are basically doesn't exhaust the ability of LLMs to learn something, right? Even for the relatively small models with 7 billion parameters. So if you don't have that much tokens, if you don't have at least 1 billion tokens, it's probably better that you don't do the training of large language models from the scratch, but you should basically take one of the existing ones and then just fine tune it for your specific language, let's say. There's also a problem with tokenization. So for example, here I have an example of the Slovene. So we see that this is the average number of tokens per word. So for example, Llama, which is a typically English model, has a little bit of multilingual abilities, but you see it on average, it uses, let's say, somewhere between 2 to 4 tokens per word, while specific Slovene models like these ones, right, they use, let's say, 1.5 words on average per word. So that means that these models are less efficient, and it would make sense that when we adapt this model, that we also change the tokenization so that this will be more efficient and that we will need less data for that. So yeah, so we have some techniques to do that. There are some techniques to do that. So for example, from Slovene language model called GAMS, so generative model for Slovene. What we did, we took one of the existing models and adapted to the Slovene with several types of the data, like news articles, academic works, web crawls, and we also took a little bit of data from other neighboring languages, from the languages which are somehow similar. And to prevent, let's say, forgetting of the English, we also took a little bit of English text. And if you want to do that, it's probably a recipe which is pretty much common, right? So how do we did it? You need quite a supercomputer for that. So we took, for example, in this case, Slovene high performance. We used basically 4 NVIDIA 800 GPUs with about 40 gigarams per node. And we use 16 nodes at once with tensor parallel length of 4. That means one model was split across one node. We used NVIDIA NeMo framework, and it took around 16 hours. So of course, this is just for one model. We had to build around 10 different versions before these things really started to work, that we could experiment with tokenizer, with embeddings, and so on. So yeah, we built now also larger models, like 9 billion models or 27 billion models. For this, we used Gemma 2 9 billion as the baseline. So we did a lot of pre-training. So we used European Leonardo supercomputer for that with 120 GPUs for 3 days. And it turned out to be the most successful open model for Slovene. So it's, of course, not competitive to, let's say, ChatGPT, which is 100 or 1,000 times larger in terms of performance on all tasks, but in terms of Slovene specific things, it's highly competitive. For example, or better. It's the best model right now for machine translation, for many tasks in superglue evaluation benchmark, and also for other evaluation benchmark. It's now on the top model, basically, in many of these benchmarks. So how do we do that? So first we have to align the languages. For that we used parallel English Slovene corpora, and we also used as much high quality Slovene data as possible. So in the previous test, we figured out that less quality data doesn't really count much. So we here used Wikipedia, high quality text from the corpus, and academic text like theses, PhDs, and so on. We didn't use web crawl tweets because it turned out to be, I mean, there's lots of this data, but it's not really good for general capabilities of these models. And we also use, for example, news, which are sorted by increasing time so that the model gets newer data later on. So let me also mention a few other successful techniques in the large language model. Probably in the industrial setting, the most useful one is retrieval augmented generation. So here we basically used when we generate, we basically say, okay, we don't have to generate everything from the parameters of LLMs. We can take some external knowledge, let's say companies' own data or scientific data which we have collected. So what do we need for that? We first have to have we get a query, right? And based on the query, we extract from our database, we extract relevant data. And this data is then put into the generator as the context so that it can basically produce better outputs then. Another such trick, which is another application which is useful, recently very popular, are agents. So what do we do? Basically, we have some request, let's say, to solve some business or that's a reasoning task. The agent then can call external tools. It has its own memory. It can do planning. It can do code generation, so to solve more complex, let's say, business or scientific problems. I think that I would now start to finish. I mean, I would wrap up. So let me also explain a little bit lessons learned about the high performance computing. So first one is building LLMs from scratch is computationally extremely costly. So it takes hundreds of thousands of hours on the GPUs. So that means that we basically, most of the people will build LLMs by further training existing large language models. So even here we have lots of issues, for example, to get the high quality data, web crawl has to have a lot of cleaning. Machine translation is useful. So, I mean, how we will build the vocabulary of the model is an issue. And then there are lots of issues with the parallelization. So I think that using high performance computing as they are designed right now is requires some computer science knowledge. So how to do parallelization, how to split the data across nodes, how to reduce inter-node communication, because these are so critical things that basically depend on whether the model will be successful or not, right? We also need really good, let's say, hardware. It has to have support for the 16-bit precision, right? And yeah, so there's a lot of HPC expertise there. So typically, I mean, for example, we were experimenting with different platforms. We are using, right now, we are using platforms like NVIDIA Nemo because it's basically, it has really highly optimized software for doing LLM tuning. It's faster, it's easier to do parallelization, but the downside is that there are less models available and that I mean, it's by no means just a straightforward process. It still needs some code and model tweaking before things start to run, right? So yeah, in deployment, my advice would be just squeeze everything on a single computational node if it's possible, because this inter-node communication would be really highly problematic if you want to use that and deploy it in some real-world scenario. So let me make some conclusions. So large language models are basically foundation models. They are used nowadays everywhere. So for many, many different tasks in business, in academia, I mean, for really, not just for text, also for the voice, for the video, for the images. So we can expect lots of development in this area. So there already are many useful applications. We know that transformer architecture is dominant right now, but there are some competitors coming now which may or may not replace them soon. For example, like XLSTM or let's say, I mean, there are other architectures out there. So there are many extensions, but yeah, there are also many methodological, ethical, and social dilemmas. How we will use LLMs? Will we use them? What type of biases are introducing due to the training data? For example, if we are using social media or web crawl, what are we actually putting into these models? So is this artificial general intelligence? Probably not. We are not there yet, but and probably LLMs are not the best way to go into that direction. But yeah, I think that new technologies and new models, new architectures might be more successful in that respect. This also brings us to the redefinitions of intelligence. So people used to say that, for example, when humans will beat chess, I mean, when computers will beat chess grandmaster, that there will be really intelligence. We don't think for a long time about that now, but so right now we are questioning whether ChatGPT is intelligence, whether it can write, whether writing is still the sign of intelligence. Yeah, so we are redefining and understanding much more about what intelligence is. So there's also the need for multilingual LLMs and adaptations for specific languages and domains. We don't want that everything could be done in English, right? So we want to have this also for the less resourced languages. I mean, India has hundreds of languages. You probably want to support them. So yeah, multimodal LLMs are here. And a crucial thing is also that high performance computing is really the new essential infrastructure if you want to do AI, which is unfortunate, right? Because HPCs are quite costly and they use lots of electricity as well, right? So yeah, we have new infrastructure. So AI is becoming the new infrastructure. So as the data is the new oil, AI is the new electricity. So we will have to adapt to that as scientists as well, find new ways how to do science, how to do it more efficiently, how to build new generation of tools for science and for business. And this is happening right now, right? So AI is being put into many machines, and yeah, that's what is going on. Let me just briefly mention another thing. So we have established a Center of Excellence in Artificial Intelligence for Digital Humanities. And so what we want to do, so we basically want to, let's say, empower digital humanities researchers in a really wide sense. So that means social sciences, philosophy, uh, histography, and so on. We want to empower them to do things with AI, right? So we built a center and we basically intend to hire people, to host people, to basically offer research opportunities, offer collaboration opportunities. So if you are interested, you can contact us and maybe we can do something together in that respect. So we also plan to do some education and offer computational support. So Slovenia has a new basically supercomputer in the creation, and yeah, we can offer some support in that respect. So we are also hiring right now. By the end of this month, we are intending to, there's a call open for 2 PhD students and 1 postdoc researchers. So yeah, let me finish here. And I think there's some time for the questions.
Hello. Thank you,
Yes.
Marco, for your great lecture. And my small couple of questions, which is like you have mentioned like several challenging steps in developing LLM models. My question is like when we do like in tokenization part, pre-processing part, and developing the model, and then again the computational problem. So for a researchers like who don't have much computational resources, what you will suggest that what they can do in research, like how they can contribute maybe on having a small language model and then try to see the impact of pre-processing or I mean, what is your suggestion to them to who don't have much computational resources and want to contribute in the field of large language models and all? Because when we work in India, most of the researchers they don't have that much of computational resources whenever they try to fine tune develop any model based on the large language model, so they stuck somewhere because of the computational resources, GPUs and all. So what is your suggestions, like if it is required anyhow, or do you think some such problems which can be taken care by the researchers who don't have sufficient computational resources?
Yes, yes. I mean, there's a whole area of, let's say, research and also practical application for the making LLMs more efficient. I think there's make them useful, let's say, on smaller devices, on CPUs. So I think there's a lot of computational know-how necessary for that, and I'm sure that I mean there is opportunity to do impact here, I think. And another one is that I mean LLMs are here as foundation models. We can all use them, we can all adapt them, It's many of them are publicly available, so basically we don't have to. I mean, everybody doesn't have to build them, right? So there are efficient techniques like LoRa or QLoRa, so quantized low rank approximation. So this is not difficult. Right? This is something which one can do on a CPU computer or a single GPU, let's say in a few hours. So definitely there is lots of opportunity. I think even if you don't have HPC, but yeah, if you would want to develop really new, let's say, architecture and so on, then you would really need supercomputers. I think that there are not many academic researchers, if any at all, who can compete with these huge companies which are, let's say, building models and trying new architecture. I think this is now entirely, let's say, for the really huge multinationals like Google, Meta, and so on, that nobody else can compete with them.
Yeah, of course. Yeah. My another question is like maybe it is very naive. What do you think, like based on your experiments? I know that you have done a lot on the tokenization part, like pre-processing part for preparing the language and the text to be good enough to train the model. So what do you think, is it a very important step that instead of without taking care of any pre-processing and just feed the data without taking care of the data quality, and then we do it with pre-processing and focusing on tokenization. So do you think it will significantly impact the overall performance of the model, or it will just like 2, 3, 4% will be the like improvement in the.
Yeah, I mean, tokenization is probably not that much important, right? So that's more or less. I mean, if you have let's say, multilingual tokenization, let's say from the llamas or from the, let's say, Gemma and so on, I think that's quite good, I would think, for most purposes, right? Unless you want to squeeze 3%, as you say, out of the models. But data quality is important, right? So data quality is really a very important issue. And there is, for example, when we are building these Slovene large language models, so we put maybe 50% of the work into the data preparation. And we did a lot of experiments with, let's say, using better data, a little bit more data and of less quality. And basically, the quality seems to be the most important issue, right? So if you can get high quality data into the models, then you will get considerably better and more consistent and more robust results than if you are just putting everything in.
So any other questions from the participants or anyone else, please?
There is one question in the chat box, if you can see.
Okay. Yeah, so there's a question from Pooja, who asked, what is the importance of the square root in the attention mechanism, and what happens if we ignore multiplying this factor? So this is I mean, there have been some research on this factor. It seems that the weights are overly increasing if we don't normalize them, right? So people have been trying also other factors, not just square root, but this is the default, and it seems to work best. I mean, lots of things in the transformers are just empirically figured out, right? So this D of K factor is one such factor. So people have been trying without normalization. It doesn't work that well, right? So they decided to, because we have so many multiplications there, we also have to normalize, right? Otherwise, we get just too large results, and then we have problems with the weights. To store them, for example, you have to know that all this is happening in a relatively limited numerical space. So, for example, most of LLMs are trained in the 16-bit precision, right? So we don't want to go to exceed that number range, right? So that's why we need also these normalizations.
Now, madam, think if there is no questions, we can close.
Yes. So no more questions, I think. So with this, we would like to extend a heartfelt thanks to Professor Marco for sparing time and